In section 4.4, we study tipping points. In this video, I'll define the idea of a tipping point and explain how to identify them. I will also present an example that highlights connections between tipping points, feedback strength, and parameter sensitivity. Let's start with a definition. A tipping point of a system with a parameter is a point at which one or more possible equilibrium states of the system makes discontinuous jumps in response to a small change to the parameter. We can investigate this idea in the phosphorus example that we've worked with several times. Recall that in this system, phosphorus inflow to the lake is generated by two things. One, the plant and algae life in the lake, which takes up phosphorus from the lake bed and creates the amplifying feedback loop on the left. And two, pollution from the surrounding land, which is represented by a parameter P. Outflow is proportional to the amount of phosphorus in the lake, creating a stabilizing feedback loop. The plot shows inflow and outflow when the parameter is at 15 tons per year. In this scenario, there are three equilibrium points. A and C are stable, whereas B is unstable. We can think of the equilibrium at A as a low phosphorus level with corresponding low levels of plant and algae life. The equilibrium at C represents a high phosphorus level with corresponding high levels of plant and algae life. High levels of plants and algae can lead to a situation where oxygen levels are low enough that animals can't survive in the lake, referred to as eutrophication. Here, I've shown inflow curves for several different parameter values. The green curve corresponds to P equals 15. In this case, we've already seen that there are three equilibrium points, marked A, B, and C. As P increases, the inflow curve will shift from green to magenta. In the process, the equilibrium points at A and B will move closer together. At P equals 28, shown in magenta, A and B will merge into a single equilibrium point, which is no longer stable. The high phosphorus equilibrium will remain. Then, for parameter values above 28, there will only be one equilibrium point. This will be a stable equilibrium at the high phosphorus level. This means that even if the lake was in a stable equilibrium level at the low phosphorus level, if pollution levels rise above 28 tons per year, the lake will be forced into the high phosphorus equilibrium. Thus, we found a tipping point for the low phosphorus equilibrium at P equals 28 tons per year of pollution. A similar situation occurs as the pollution drops to very low levels. Here, as the pollution level approaches 10 tons per year, shown in orange, the equilibrium points at A and B approach one another and merge. For pollution levels below 10 tons per year, there is a single low phosphorus stable equilibrium. So we're getting another tipping point at pollution levels of 10 tons per year. Another way of understanding tipping points is analyzing strength and sensitivity. As the system approaches an equilibrium, we expect the total strength of the stabilizing feedback to approach zero. Equivalently, the sensitivity of the equilibrium to changes in the parameter becomes large. This allows us to predict tipping points by looking for weakening on the stabilizing feedbacks or by identifying a sluggishness in the equilibrium in response to changes in the parameter. Let's return to the phosphorus example to see these ideas at work. In the graph, I've shown a zoomed-in view of the high phosphorus equilibrium, which experiences a tipping point at 10 tons per year of pollution. I've included inflows for several pollution levels near this tipping point and calculated the strength of the feedback loop and sensitivity of the system at the resulting equilibrium point for each pollution level. Recall that the strength of the feedback is a measure of how much the flow rate changes for a small change in the stock. In this plot, notice that as you move from green to orange to magenta, the inflow curve gets closer to the outflow curve. This results in a net flow that is closer to zero, which is reflected in the strength getting smaller. To understand the changes in sensitivity, recall that sensitivity measures how much the equilibrium point changes for a small change in the parameter. In this plot, a change in the parameter corresponds to the shifting the inflow curve slightly up or down. If we move each of these curves slightly, the magenta equilibrium point will experience the biggest shift to the right. This is reflected in the larger sensitivity measure. Although scientists often don't have definitive models of systems, measuring changes in strength and sensitivity provides one tool for trying to predict tipping points.